So far, we have been working with radians. Now we'd like to know how to convert to degrees. We know if we go all the way around the unit circle, that corresponds with 2 pi radians. We know a full circle corresponds as well with 360 degrees. Therefore, if I'd like a conversion factor, what if I divide both sides of this by 2 pi? That means every 1 radian corresponds with 180 over pi degrees. And I can use this as a conversion factor. So let me convert some angles now to degrees then. What about the angle theta equals pi over 3? So I know I can convert this by multiplying by my conversion factor, 180 over pi degrees. That means that pi thirds corresponds to 60 degrees. What about something a little more interesting, like negative 3 pi over 10? Same idea, so I have an angle here in radians. I will multiply by 180 over pi degrees. So that leaves me with what? Negative 3 times 18 degrees, which is negative 54 degrees. Not so bad. So what about vice versa? Well, same idea. I know again that 2 pi radians corresponds with 360 degrees. So if I want to know what 1 degree corresponds with, this time I would divide by 360 degrees. So that leaves me with conversion factor this time of pi over 180 degrees. So let's see then. What if I had an angle then, and this time I want to convert to radians? What about something simple like 90 degrees? So again, I would multiply by my conversion factor, this time pi over 180 degrees. And that's a simple one, so that would give me pi over 2 in radians. Should I do one more? What about negative 25 degrees? So again, I have an angle in degrees, so my conversion factor would be pi over 180 degrees. So I would reduce my fraction, divide by 5, so what is that? Negative 5 pi over 36 in radians. what about finding some coterminal angles? Now these are just angles that share a terminal point. In other words, they land at the same spot on the unit circle. So for example, the angles 0 degrees and 360 degrees are coterminal. So what if I have, for example, an angle like theta equals 60 degrees? So I could locate this point on the unit circle. So all I'm looking for here, I'm looking for angles that will land me at the same spot here as 60 degrees. So I guess if I start at 60 degrees, every time I go around the circle, that's adding or subtracting 360 degrees, I land back at the same terminal point. So what if I just take my angle, 60 degrees, and I add multiples of 360? So 420 degrees, let's see if I add another 360 to that. What is that, 780 degrees? Add another 360. What is that, 1140 degrees? So I've found 1, 2, 3 angles that are coterminal with 60 degrees. Let me find a few more. So what if I take my 60 degrees and I instead subtract 360 degrees? There's another one then, negative 300 degrees. So you can see if I start here and go negative 300 degrees, I'm here, right? Because if I went another 60 degrees, I'd be here. Then I could subtract another 360. So that'd be negative 660 degrees. So I could actually find infinitely many of these. So here I have 1, 2, 3, 4, 5 angles that are coterminal with 60 degrees. So this will be, I guess, my number 1. So what about on number 2? What if I have an angle that's in radians? Like maybe, oh, I don't know, pi over 6. Now I guess I could convert this to degrees, but it's really not necessary. So I'm looking again for coterminal angles. So if I'm thinking in radians, still maybe locate pi 6, that's here. Instead of adding and subtracting 360 degrees, I would just be adding and subtracting 2 pi. So that'll send me all the way around the circle in one direction or another. So my coterminal angles, let's see, first one I'd have pi 6, and I would say add 2 pi. So I have to find a common denominator. So if I multiply by 6 over 6, I guess then what I'm doing here is I'm taking my angle and I'm adding multiples then of 12 pi 6, because that's 2 pi written in 6. So the first angle coterminal with pi 6 would be 13 pi 6. That makes sense because if I go start at 0, if I go 12 pi 6, I'm back at 2 pi. So another 1 pi 6, I'm here. So there's my first coterminal angle. So then, I mean, I could take 13 pi 6 and add another 12 pi 6. That would give me 25 pi 6. There's another one. I guess the next one would be 37 pi 6. Okay, now remember I could also subtract. So what if I have pi 6, then I subtract 12 pi 6. That would be negative 11 pi 6. So let's see if that makes sense. So if I start at 0, if I'm going in the negative direction, I'm going clockwise, 11 pi 6 would land me there. It looks correct. I could subtract another 12 pi 6. That'd be what, negative 23 pi 6? There's that one then. So let's see what else is in this section. So there are a couple of formulas. So one of them is for finding the area of a sector. So what does that mean? That's like if I have a slice. So if I have, a circle here, if I want to find the area of one slice here. So I can kind of come up with this formula pretty easily as well. So here's the way I think about this. So let me start by saying, well, what if I think about a full circle? So then I would say, if I were to go all the way around the circle, let me think in radians. I would have gone 2 pi radians, right? And I know for a full circle, I can find the area using the formula pi r squared. So then again, I would say, well, what if I want to know what 1 radian corresponds with? So I would divide both sides of this by 2 pi. So that tells me that every 1 radian corresponds with, what would that be? 1/2 r squared as far as my area. So what I've actually found here is really a conversion factor. So to find my area, I would use this conversion factor. I would say whatever my angle is, I would take it and I would have to multiply it by 1/2 r squared, since that's my conversion factor. So the only thing I have to be aware of here is that this angle theta, when I derived this formula, I used 2 pi for the angle all the way around the circle. That would mean that I would need to have my angle theta in radians, because I used radians here when I derived this formula. So whenever I use this formula, my angle must be in radians. But otherwise, here's my formula for finding the area of a sector. So let's see what we can come up with then. For an example, let's say find the area of the sector. Okay, so I'll try to do a decent circle. So I have a circle here. Let's see. So how about a radius of 7? And let's say the central angle here is pi over 3. Okay, in case you can't read that, let's see, my angle, central angle is pi thirds. So if I want to find the area of this sector here, this slice, all I have to do is use my formula. So it's actually just 1/2, let's see, it's r squared, so that would be 7 squared, times theta, which was given in radians. So what would that be? That would be 49 pi over 6. So I didn't put units here on the 7. I don't know, say I said this was 7 feet. Well, in that case, then this is the area, so this would be in square feet. So, I don't know, you can think of this as a decimal. This is like 49 times 3.14 divided by 6. So that would be giving me the value of the area of that sector. So what about one more? What if I have a circle? What if I know the radius here is 4? How about my central angle 50 degrees? And I again want to find the area of that sector. So I would apply my formula, 1/2 r squared times theta. The only thing here is the theta is actually presented in degrees. So because I derived this formula using radians, remember I'm going to have to first convert my angle 50 degrees into radians, but I know how to do that. I would multiply it by my conversion factor, pi over 180 degrees. So what is that? 5 pi over 18? So that goes back in my formula for the area of a sector. Then I just have to see if I can simplify this. So let me see here. What is this? 16 divided by 2? So what am I left with? 8. And then 5 pi over 18. Can I divide top and bottom by 2 one more time? So I guess it would be 2. Or rather 8 divided by 2 would be 4. And then I'd still have 5 pi. If I divide 18 by 2, that's what, 9? So looks like, what, 20 pi over 9? And then if I didn't put units here on the radius, then I would just assume I had generic units there. So let me say maybe square units, units squared. There's my area of that sector. And there's only one more formula in this section. It's actually an even simpler formula. And this is the formula for finding arc length. So, again, I can start this the same way. So when I'm thinking of arc length, I'm thinking of, okay, so if I have a circle here, if I have a slice again, now instead of finding like the area of this sector, what if I wanted to know what portion of the circumference I have here? Like, in other words, if I was going to fence this piece of the circular field, how much fencing would I need to put from here to here? So the letter S is typically used for arc length. Okay, so I can derive this formula in a very similar fashion to how I derived the formula for the area of a sector. So again, I'm going to start by thinking about a full circle. So again, if I was to go all the way around the circle, thinking in radians, that angle would be 2 pi. Now, I know if I was to go all the way around the circumference of the circle, I would have traveled the entire circumference of the circle, right? In other words, if I use the angle 2 pi, I've gone all the way around the circle. So the arc length would actually just be, well, the circumference of the circle. So I know the formula for the circumference of a circle, it's just 2 pi r. So actually this formula is going to turn out nice and simple. So I'm going to, again, divide both sides of this by 2 pi so that I know that every 1 radian here corresponds with an arc length of, well, just r. So I actually have my conversion factor and a formula for arc length. So all we have to do is take our conversion factor r and multiply it by our angle theta. Now, again, I use the angle 2 pi here rather than, say, 360 degrees. So I'd have to say that, again, theta must be in radians in order to use the formula here for arc length. But other than that, it's really pretty straightforward. So let's see, how about find the arc length. And here's a number 1. Here's the radius, how about 6? And here's the angle, the central angle here, 2 pi over 3. And my goal is to find the length of this arc here. We'll call that S. So I know I can apply my formula, S equals R times theta. This one's very easy because my angle theta is already in radians. So let's see, 6 divided by 3 is 2. 2 times 2, 4 pi. So I don't know, if I had some units, maybe I'll say 6 feet here. Then this would be the arc length in, well, feet. So I don't know, as a decimal, it's like 12 point something. So I'm saying I would need 12 point something feet of fencing to fence this portion of the circle here, say. Okay, so what if I had something like this? So here, let's see, my radius is 3. Okay, let's see what else I know. So this one, let's see, this one tells me the radius is 3, and it tells me this angle here is 160 degrees. But this one has a catch. What we actually want to find in this case is the length of this arc here. This is the arc S. So actually 160 degrees is not the central angle. I guess the central angle would actually be, let's see, 360 minus 160. So that central angle would actually be 200 degrees. So that's the first thing. But then I go, okay, well, to use my formula, remember this angle must be in radians. So because it's in degrees now, I have to use my conversion factor, pi over 180 degrees. Let's see, so what is that? 20 over 18, 10 pi over 9? That's my angle now in radians. So now I can apply my formula. So it's R, let's see, R was 3, and then times theta. 10 pi over 9. So that would be what, 10 pi over 3? You know, again, if I didn't put units, I could use the generic. Let's see, this would be in whatever the units were. So again, I'm thinking like if I were fencing this portion here, let's see, this is like 10 times 3.14, so it's like a little bit more than what, 30 divided by 3, so 10 point something units of fencing that I would need. Another piece of paper. So I could do one more. It's probably not necessary, but what if I wanted to say, find the central angle, theta, given some information. So let me see, I have another circle. Here's my circle. What do I know? I know the radius is 4, and my goal, let's see. My goal will be, okay, kind of drawing a generic sector here. My goal is find the central angle theta. If I know the length of the arc here is, let's say, 10. Okay, so I know my formula, S equals R theta. So let's see, I know my arc, that length is 10. I know my R is 4. I'm looking for theta, so this is very easy. So I would actually just divide by 4. So 10 over 4, therefore my theta is 5 over 2. So this would be in radians because my formula here for arc length is in radians. So how the heck would I locate an angle like 5/2 if I was to say graph that? Well, with radians, I'm used to thinking of those in terms of pi. So if I have something here that doesn't actually have the pi in it, I kind of have to think of pi as a decimal. So let's see, pi would put me here, right? Pi radians from here to here. Well, I know that pi is approximately 3.14, right? So actually that means here, I know this is pi over 2. So I don't know, what's half of that? 1.55-ish. So if I'm looking at an angle like 5/2, what is that? 2.5? 2.5? Well, I know 2.5 is in between 1.5 and 3.14. So I know at least that this angle is somewhere here, you know, in quadrant 2. Theta equals 5/2. But I guess I could, you know, if I wanted to, I could convert this to degrees. Not really necessary. But what if I take 5/2 and multiply it by 180 degrees over pi? Okay, what would that be? 180 divided by 2 is 90 times 5. So what is that? 450 degrees over pi? So what is this? I mean, this is like 450 degrees, you know, divided by 3.14. So what is this? A little bit less than 150 degrees. So really, either of these would be an acceptable answer. I would just leave the answer like this. But if you think about this one, this is like 150 degrees or so. Let's see. This is what, 90? This is 180. So again, 150 degrees would be here in quadrant 2. So it seems like we've gotten that correct.